Okay, we're working on page 2 of the review for your test on three-dimensional geometry and measurement. Problem 5 says the picture shows a toolbox with a black handle. Which drawing best represents the top view of the toolbox? So if you were looking from the top, what would you see? You would certainly see this black handle, so we could rule out answer choice B. And the black handle would be centered, so it must be D or A. There's a tendency for students to think that this curved part of the toolbox would show up in some views where it actually wouldn't. If you were looking directly down from the top, you were standing over this toolbox and looking straight down at it, this section would look like a straight line. A straight vertical line, just as you see here, as would the right side part from the top. In fact, you wouldn't be able to tell that this piece was curved from the front view either. You would only know from the side or from some kind of isometric view like we have here that this curve exists. And so the correct answer here would be D for the top view. Problem number 6 asks us to find the surface area of this solid. First, we should think about what is the solid. You're looking for, it's probably either a pyramid or a prism. It doesn't look like it can be a pyramid because I don't see a single base going to a vertex. It looks like it must be a prism. And then you need to ask, what are the bases? These top and bottom faces are parallel rectangles, but they're not congruent. The parallel congruent faces would be this trapezoid and this trapezoid. So, this would be the base right here, as would this congruent trapezoid back here. And so we should, in order to find the surface area, there is no formula for surface area. It's just a matter of finding the area of each of the faces and adding them all together. In some cases, we could multiply the area of one face by 2 or more, depending on how many congruent faces we have. For example, if I call the trapezoid face A, I don't need to calculate the area of this face A back here because these are parallel and congruent, and so I could just double this area to get the area of both of those trapezoidal faces. So what I'm going to do is sketch face A here. I know it has a 5-foot base up here, an 8-foot base down here. You see you can't see the 5 here, but you see it back here. And then this height is it's not shown here, but you have perpendicular side here, so that the perpendicular distance between the bases is 6. And so the area of face A, we would use the trapezoid area formula, which is 1/2 multiplied by the sum of the bases being the 2 parallel sides, multiplied by the height of the trapezoid, which is the perpendicular distance between the bases. So the area of face A is half of 8 plus 5 multiplied by 6, or 1/2 multiplied by 13 multiplied by 6. I'm going to choose to associate and take half of 6 as 3, and then multiply 3 by 13, I get 39 for the area of face A. I'm going to call face B this bottom face, and then I'm going to sketch it right here. Face B is a rectangle. It has a base of 8 and a height of 12. And I don't think we need to write the formula for area of a rectangle. We just know it's base times height. 8 times 12 is 96. So the area of face B is 96. I'm going to call face C this diagonal face right here. So I'll sketch it here, face C. It has a base of 6.7 and a height of 12. So base times height will be 6.7 times 12, or 72 plus 8.4, which is 80.4. So the area of face C is 84. Now we've accounted for the two trapezoidal faces, this diagonal face and this bottom face. We still have this top face and the back face. I'm going to call the top face D. This top rectangle D. Sketch it down here. D is 5 by 12 for a total area of 60 for face D. And lastly, face E will be this back face. Back here. Face E, another rectangle. It's got a height of 6 and a base of 12 for a total area of 72, 6 times 12. Okay, then the question is, you know, how do we put together a formula for the total area? The total surface area will just be the sum of all these areas, but we have to keep in mind that we have to double face A because I have two of these trapezoids, two parallel and congruent bases. So it's going to be 2 multiplied by the area of face A plus the area of face B plus the area of face C plus the area of D plus the area of E. So the surface area, total surface area of the trapezoidal prism will be 2 multiplied by 39 plus 96 plus 84 plus 60 plus 72. That's 78, and these go together nicely because the 6 and the 4 is 10, 10 and 90 is 100, 180 is 180, plus these two added together is 132. And these go nicely together because the 8 and the 2 is 10. So I have 140 and 70, 210 plus 180, 390 square feet would be the total surface area if I've done it right. I haven't. What did I do wrong? Area C is not 84, it's 80.4. Well, that's unfortunate. Okay. Let's try this out. Okay, this should have been This should have been 80.4 plus 60 plus 72. So this is 78 plus 96 plus 80.4 plus, let's just add these, 132. 70 and 90 is 160. 8 and 6 is 14. So 160 and 14 is 174 plus 80 and 132 is 212 plus 0.4 is 212.4. If I add these together, I get 386.4. 386 and 4/10 feet squared. Okay. So if you have a surface area problem, you just find the area of each face and add them all together. Just look for opportunities like congruent faces so you don't have to do extra work. Problem 3 asks us to provide the most specific name for each of these shapes. These spaghetti containers have hexagonal bases. They have parallel congruent bases. Two bases that are parallel and congruent indicates a prism. And since the shape of the base is a hexagon, this is a hexagonal prism. This is clearly a pyramid. We have a single base and then it goes to a vertex. I suspect that this is a square base, but since we can't see the whole square, if you said square pyramid or rectangular pyramid or triangular pyramid, I would accept any one of those three. But I believe it's a square pyramid. This cookie container is a prism because the top and the bottom are parallel and congruent bases. There are two bases. In the pyramid here we only had one base, one square base. The main difference between a pyramid and a prism is pyramids have one base, prisms have two bases. So we have two parallel congruent bases here. They're octagons, so this is an octagonal prism. Finally, we have a cone. Has a circular base and then it goes to a vertex. It's like a circular pyramid in a way. Cone. Problem number 8. We need to name each polyhedron, then count the number of faces, edges, and vertices. Lastly, we'll use Euler's polyhedron formula to verify our counting, our results for a number of faces, edges, and vertices. This solid has two bases. They're parallel and congruent, so it's a prism. And since the bases are five-sided polygons, it's a pentagonal. Get a better color here. Pentagonal prism. The faces, the two bases count as faces, so there's two, and then there's 5 more faces to connect those two bases. So that's a total of 7 faces. The edges, there are 5 edges making up each base, so that's 10 edges already, and then 5 more edges connecting the vertices of the bases. And so we have 5, 5, and 5 for a total of 15 edges. There are 5 vertices for each base, and that's it for the vertices, so there are a total of 10 vertices. I'm going to use this formula each time in this, I haven't given you a lot of room here, but in this empty space, so the number of faces 7, minus the number of edges 15, plus the number of vertices 10 should be 2. 7 minus 15 is negative 8, plus 10, negative 8 plus 10 is 2, so that's how we check using Euler's formula. This next solid has a single base and then it goes to a vertex. All the other faces are isosceles triangles going to that vertex, and so it's a pyramid, and since the base is an octagon, it's an octagonal pyramid. The number of faces, the base counts as one face, and then we have 8 more faces going to this vertex. So we have 1 and 8, for a total of 9 faces. There are 8 edges on this octagon, and then there are 8 more edges going to this vertex, so there's a total of 8 and 8, or 16 edges. The number of vertices would be 8 on the octagon, and then this single extra vertex at the top of the pyramid, so we have 8 plus 1 for 9 vertices. Substituting into Euler's formula, we have 9 minus 16 plus 9. 9 minus 16 is -7. -7 plus 9 is 2. And so that satisfies Euler's polyhedral formula. This one's a bit tricky. We have parallel rectangular faces here, but they're not congruent. They're not parallel and congruent. Doesn't look like a pyramid. If you look at this face, this trapezoid, there is a parallel congruent trapezoid on the back. So if you look at the front and the back as the bases, you'll see that this is a trapezoidal prism with the 2 bases are faces and 4 more bases for a total of 6 faces. There are 4 edges on each base, so that's 8 edges plus 4 more connecting them, like there. So there's 4 and 4 is 8, and 4 more is 12. 12 total edges. There are 4 vertices on each base for a total of 8 vertices. Faces minus edges plus vertices should be 2. 6 minus 12 is a det of 6. And a det of 6 and 8 is +2, so that checks. Here we have a pyramid. We just have a single base, and then it goes to a vertex, and so it's a pyramid. The base is a triangle, so this is a triangular pyramid with a total of 1, 2, 3, 4 faces, 3 and 3 for 6 edges, and 3 plus 1 or 4 vertices. Bases minus edges plus vertices should be 2. 4 minus 6 is -2, and -2 plus 4 is 2. So that all looks good. And that completes page 2 for the review. We'll pick up the review with page 3 and problem 9 on the next video.